Hi folks, we're going to take a quick look today at Newton's method. We're glossing over a lot of what's in 5.5, but this is just too good to skip. You may have wondered how your calculator comes up with great approximations for difficult calculations quickly. And this is one way that some calculators or some computing machines do it. It's a method that's iterative, which means that you do a process and you come up with an approximation, and then you do it again and you come up with a better approximation, and so on until you're correct to however many decimal places you want to be. Okay, so Newton's method solves anything. It's used to solve equations in the form f of x equals 0. And what we mean by solutions graphically are values that make the function equal to 0. Okay, so if this is f of x over here, this is a place in blue where f of x equals 0. It's an x-intercept. So we have to think graphically in order for this whole thing to work. So we're looking for x-intercepts on graphs, essentially. These x values are called roots, x-intercepts, or sometimes they're called zeros of the function. And there are some types of equations that we can already solve really easily. So linear, if we've got y equals mx plus b, that's easy to solve for any value. Quadratic, so ax squared plus bx plus c. We've got a lot of ways to solve that, whether it's completing the square, factoring, or quadratic formula. Exponential, so that's stuff like a to the x or equals some constant, or e to the x equals some constant. We can solve those with logs. And something like this, power equations, so x to the n could be x to the 5, x to the 9 equals some constant. Those are easy to solve as well. You just take a root. Okay? Those solve pretty easily. But there's stuff beyond quadratics, of course. There's third and fourth degree polynomials. They have complicated formulas that are probably not worth the trouble. Fifth or higher have no formulas. And it's not that we haven't found them. There can't be formulas for them. So we need a better method. Newton's method approximates roots for different equations. So here's what might happen. Is you've got some curve like this. And right here, there's the root. That's what you're looking for. You don't know exactly what value it has. So what you do is you take a guess. You call that guess x1. And it shows up here on the curve. And from there, you can draw the tangent. That's easy with calculus. And guess what happens? That tangent has an x-intercept. And that x-intercept is a slightly better approximation of the root. Whoa. But let's not stop there. If you go to that better approximation and you make its tangent, it has an x-intercept, which is an even better approximation of the root. And you can keep doing this and get successively better approximations and closer to the actual value of r. It's always going to be approximation, but it's going to be a darn good one. So r is the root, x1 is a guess. Tangent lines get closer and closer to the root. They're x-intercepts. So you go and find x2. Let's think about that. Here's the point slope formula. Y minus y1 equals m x minus x1. Let's suppose we were talking about a second point on that line too. So this is really just a rearrangement of the slope formula. So we're talking about two different points here. Okay, if I wanted to find x2 on this, that means x1 and y1 are given. They're pretty straightforward. If I were to do it in function notation, I'd write it this way. y1, that's f at x1. Okay. The slope, slope, that's the slope of the tangent. So it's f prime at x1. Okay. x2, that's going to be the x-intercept we're looking for. And x1 is our initial guess. Now if I'm looking for an x-intercept, that means that y2 right here is 0. Let's see if we can solve that for x2. Okay. So on this side I'd get negative f of x1 equals f prime of x1 by x2 minus x1. In my next step, I might divide by f prime, so I'll get negative f of x1 over f prime of x1 equals x2 minus x1. Wow, or x2 equals x1 minus f of x1 over f prime of x1. That is the next x-intercept as we go through this process. Now, if you took it a step further, same thing will happen for x3. If you want the next x-intercept, it'll just be x2 minus f of x2 minus f prime of x2. Or generally, okay, the n plus 1th x is going to be x to the n, or xn rather, of f at xn minus f prime of xn. So you can do this process, then you do it again and again, and very quickly, if you have a good first guess, you're going to get a great approximation. So note, good first guess is necessary. Often first guess is given or interval is listed. We're going to quickly set this up for a couple little questions and just get the hang of what it looks like. Okay. Example 1. Find a root for f of x is x cubed plus x1 plus x plus 1. And x1 is negative 1. Okay. So that means, here's the formula. Xn plus 1 is xn plus f at xn all over f prime of xn. In this case, f prime of x is pretty straightforward. It's 3x squared plus 1. So if I have x1 is negative 1, what I need to do to find x2 is put in x1 minus f of x1 over f prime of x1. Okay. And I'm going to do that on the calculator. Now, it's super easy with negative 1. But we'll do it this way anyways, because when the numbers get messy, we want to be able to use the calculator. Okay, so that's going to be x1 was negative 1. So negative 1 minus brackets f of x1, that is brackets negative 1 cubed. Cubed. Plus negative 1 plus 1. Okay. All divided by f prime at negative 1. So that would be, again, brackets to make sure the calculator knows what I'm talking about. I'm just putting in numbers into the derivative function. Okay, I press enter, and it gives me an approximation of negative 0.75. Let's write that in. Negative 0.75. Okay, from there, finding the next one is actually not so bad. So x3 is going to be x2 minus f at x2 over f prime of x2. Okay. Thankfully, my calculator has an answer button, so I can just put in the answer that I just had minus. on top, I've got answer cubed plus answer plus 1, all divided by, open brackets, 3 times answer squared plus 1. Negative 0.686-ish. Okay. Now I'm only going to write down a few decimal places, but I'm going to keep them all in my calculator. Okay, now I'll do it again. x4, so that'll just be the answer that I just found, minus answer cubed plus answer plus 1 divided by 3 times the answer squared plus 1. Oh, that's not actually a big difference. Negative 0.682. Okay. And let's keep going. Answer minus answer cubed plus answer plus 1 divided by 3 times answer squared plus 1. Wow, pretty close to the same. In fact, we can say with pretty good certainty that this is correct to at least 3 decimal places, at least 4 really, decimal places, the right answer. Okay. Now if I go and actually graph it and look for that root, let's see, what do we have here? X to the power of 3 plus x plus 1. Here's what it looks like. It does look like it has a root or a 0 around negative 0.5-ish. And if I use the calculator to find it, the left bound is negative 1, right bound is 0. My calculator says it's negative 0.6823, which is what we just found to 4 decimal places. Okay? So again, it's an iterative process. That means you do the same thing over and over again. Let's try it for example 2, which is y equals x to the 5th minus 10, and x1 is 1.5. x5 minus 10. Okay, so again, we're going to need the derivative, which is 5x4. Okay. And if I write out what's going to happen for the first one, it's going to be x1 minus f at x1 minus over f prime at x1. Let's do that. So 1.5 minus, the first one takes the longest to type in, 1.5 to the power of 5 minus 10 divided by 5 times 1.5 to the power of 4. Close, close. Gives me 1.595, roughly. 95. Okay, and now we just do it again. So use that answer minus f was just x to the 5th minus 10, so answer to the power of 5 minus 10 divided by 5 times answer to the power of 4. 1.585. Let's do it again. Answer minus answer to the power of 5 minus 10 divided by 5 answer to the power of 4. $1.58489. Wow, we're getting pretty close here. And how we know we're doing a good job is that the numbers aren't changing very much. Okay, they're very close. Let's do one last one. Answer minus answer to the power of 5 minus 10 okay, divided by 5 answer. Sorry, I'll put brackets around that. 5 answer to the power of 4. Wow, hardly any change at all. We've got it not changing for 1, 2, 3, 4, 5, 6, 7 significant figures. And that's for a question that would otherwise be pretty much unsolvable for us. We just don't know what the value is. Let's really quickly check out the setup for the next one, which is asking us to find the square root of 7. Okay. So number 3 is slightly different. We want to find the square root of 7. That's not really in a function form. And it's rough to deal with because root 7 is not a pretty number. But it's equivalent to x squared equals 7. Or x squared minus 7 equals 0. That is the function that we turn this into. So we turn it into a nice equation that's equal to 0. The function becomes x squared minus 7. Okay, y prime is going to be 2x. And let's estimate. Let's see, square root of 4 would be 2. I don't know. Maybe try x1 halfway between 2 and 3. Maybe a little closer to 3. I'm going to try 2.6. Okay, that's my guess for the square root of 7. Now I want to find it correct to a bunch of decimal places. So x2 is going to be x1 minus f of x1 all over f prime of x1. Okay. For this one, that means 2.6 minus brackets 2.6 squared minus 7, close brackets, divided by 2 times 2.6. Okay. And we get 2.646. Okay, so x2 is 2.646. And keep going. Just do it again. Use the answer. Minus the answer squared minus 7 divided by 2 times the answer. And if it doesn't change much, we know we're doing a good job. Oh, wow, it did not change much. 2.64575. Okay, it was still not quite correct to the number of decimal places we wanted, because it did change a little bit. Answer squared minus 7 divided by 2 times the answer. Ooh, that's looking really good. x4, just by our 4th iteration here, we had the same result. See how x3 and x4 look the same to 5 decimal places? That means this must be correct to 5 decimal places. If you want more accuracy, what do? You just put in more iterations. Okay, so we could do that a bunch of times. Now let's just check what the calculator says about root 7. Oh, wow. So our approximation at the fourth iteration is correct to all the decimal places that the calculator will do. It's really, really good. Okay, let's take a look at one last example here, one where we couldn't solve it analytically even if we wanted to, and where we are not given any guesses. So we want to solve cos x equals x to 5 significant figures. When you don't know the value to guess, the best plan is to start off with a sketch so that you know what your x1 is going to be, or you can have a decent idea. So let's see. Cos x looks like this. Here's pi over 2. Here's pi. That's just a portion of cos x. The graph of x looks like this. So we're asking ourselves, where do they meet? They meet somewhere before pi over 2. Let's say we can guess that this is 0.8-ish, or you could even call it 1. But it's something before pi over 2. Whereas if you choose, say, a value of 100 million, then you're going to have trouble. Okay, we've got the graph, so we know where that point of intersection is. And our method is this. We turn this into a function. So that means putting everything on one side. So we're going to solve cos x equals x by turning it into the function cos x minus x equals 0. Okay, that's what gives us our f of x. Our f prime is pretty easy to get. We'd have negative sine x minus 1. And it looks like our x1, our guess, is 0.8. I'm going to show you how to use your calculator efficiently here. So x2 is going to be x1 minus f of x1 all over f prime of x1, and so on. Or x2 would be x1 minus, let's see, f of x1 would be cos of x1 minus x1 all over f prime. That's negative sine of x1 minus 1. We can use our calculators to kind of program this in. And here's the way we're going to do it. So if you have a decent two-line display, this should go well. The first step is to tell it what your initial guess is, 0.8, and then press equals so that that becomes the answer. Now, what we're going to use in place of x1 when we input this in is the answer key. So we go answer minus, open brackets, cosine of the answer. And we do this in the very first step, minus the answer. Answer acts as x, divided by negative sine of answer minus 1. Okay. Oh, looks like we had a good guess. So x2 is 0.739. Eight, 5, 3, 3. Now to get x3, if you have a decent calculator, you can probably just press enter again, or equals again. Okay, and see how the number changed? So it iterated the process. It looked at what the next one's going to be, x3. So it did the same thing that happened when we painstakingly put them in before. Okay, I'll do it again. x4 is 0.73908513332. Now let's see, what numbers changed? Between the second and the third, we had these numbers stayed the same, but the next one's changed. On the fourth one, we had a whole bunch of digits. The first 6 digits stayed the same. So to 5 significant figures, which is what it asked us for here, we're going to say x is roughly 0.73909. Okay. Now, at this point, it's no problem to get your calculator to go further. Look, I'll have it go again. And you can see that that answer we have for x4 is actually excellent. It's taking it as far as our calculator would go. If we did this on Desmos, we'd get the same result. So let's take a look at that just briefly. We've brought up here the graph of cos x and the graph of x. And their point of intersection is the solution, and you can see right there it's 0.739. But Desmos is only giving it to us to 3 sig figs. We go further with this analytical method. And you can imagine in a time before calculators and graphing apps that this is a pretty important idea. It lets you solve very difficult things. Here's what I want you to do. Use Newton's method to solve or find roots for the following to 5 decimal places. And you can use Desmos to check, so I'm not going to give you the answers here. You can always check those graphically. You may want to copy those down, or if you'd already printed out the PDF notes, you've got them. Conditions where Newton's method may fail. If you have a horizontal tangent at your test point, well, then you've got trouble. You're not going to intersect the x-axis. If you have tangents that kind of result in bouncing back and forth between two x values, that's relatively rare. Or if your guess is sufficiently bad that you just miss a root, that's definitely possible. So ways that you can check whether you've got a decent starting value is to substitute in an x value and see if it comes close to balancing the equation. On a and b up here, we're looking for roots, so it's going to be substitute 0 in for y. And in C, we're solving an equation, and D, we're estimating the value of the cube root of 10.